Okay, in this video, we are going to derive the margin of error, right? When this equality is given. So remember, confidence level we chose was 95%. And that means the interval must contain the true parameter with 95%. And we rewrite inside the probability in this way because the probability is coming from the randomness in x bar. And we know the distribution of x bar is approximately normal distribution, right? So let's start what we can do. Remember, we know it is normally distributed, and also we know the parameters for the normal distribution. So the expectation of the sample average equals the population expectation, right? And standard deviation of the sample average equals the population standard deviation of a single outcome divided by square root of n. So standard deviation is denoted as sigma, right? And then approximated by the central limit theorem, x bar is normally distributed with mu and sigma squared over n, right? Using these two parameters. Okay? That means you need to standardize x bar as x bar minus mu over sigma over square root n. This is the standardization using these two parameters. Okay? And then we know it is approximately standard normal distribution, right? So then come back to the 95%. Remember, we need to satisfy this probability equals to 95%. And in this probability, x bar is the only random variable. So standardize it. Standardize x bar using this part, right? And we have to do the same standardization on the other sides, right? Here and there. And simply we may cancel out mu canceled out. And in the end, what we have is this one. Of course, the standardized x bar becomes a standard normal distribution variable, z. So we have, in the end, we have z, standard normal distribution, is like a plus m over sigma over square root n. So plus something, and this is same thing with minus sign, right? So minus something plus something should contain standard normal distribution, and that probability must be 95%, right? So 95% must be plus minus something, and visually, this is what we are doing. We are looking for a number a, and plus a minus a contains 95% of the standard normal distribution. That is what we want. How can we find it? We actually did some practice like this. To do this, first you have to understand that the other 5%, so 5% must be on this and that tail, and they are split evenly, equally split on each side. So lower tail has 2.5%, upper tail has 2.5%. But also what we want is a cumulative probability for A. Cumulative probability for A in the end becomes 97.5%. So still A is unknown. We would like to solve for A. Then we can calculate the cumulative probability of A equals 97.5%. So you can use normal distribution inverse formula on Excel. So using this relationship, you can find approximately A must be 1.96. Okay, and that implies originally we wanted to say this one. This is our destination, right? 95% is in between plus minus 1.96. So remember, why do we need this? Because we had this result after standardization. So this probability must be the same as this probability. So this guy, m over sigma over square root n equals 1.96. That is our result. So then, you can solve out m. M equals, so moving the denominator to the other side, m equals 1.96 times sigma over square root n. Okay? So, and n is the sample size. To calculate m, n is the sample size which is known, but the standard deviation is a problem. But we may use another estimator for the sample standard deviation. Sample standard deviation formula is written this way. So this is an unbiased estimator for the true standard deviation. So use that instead in the place of sigma. So in the end, this is how you calculate the marginal error. So again, when you have data, so you know the sample size, and then from the data you can calculate the standard deviation and plug them into this formula. Then you get the margin of error and add and subtract the margin of error from the point estimator, the sample average. That is your confidence interval. Okay? So it is combination of all the things we learned in the previous chapters. So that's why the chapter 6 and 7 are important, because they are going to they are used here. Okay? So then let's generalize it. So far we only considered 95%, so we obtained 1.96. But in general, you can write it this way. I just choose an error probability of alpha, or confidence level 1 minus alpha. You choose 1 minus alpha as the confidence interval, then you must satisfy this guy. Then following the same standardization process, you get the same formula. So this part does not change because it does not depend on alpha. So this is the same as before. You standardize and mu cancel out. Standardized x bar becomes z, and then you get this one. And again, the point is both sides, left side and right side, are the same number with different signs, right? Plus minus something. It equals 1 minus alpha. Then what you need to do here is you need to find a value a that satisfies this probability for the standard distribution, standard normal distribution, right? And it is just like if you know alpha, you can calculate that using Excel. But in our abstract solution, we are going to use this notation. Say, so because plus minus a contains 1 minus alpha probability, upside on the right side tail, there should be alpha over 2 probability, and left side tail, it should have alpha over 2 probability. So this point is top 2.5%. So 2.5%, only 2.5% is on the top, on the right side of greater than a. In this case, alpha over 2 probability is greater than a. So you may call a as the top alpha over 2 probability value, right? So if alpha was 10%, then a should be top 5% value. In that way, we are going to define this as lowercase z subscript alpha over 2. That corresponds to a, right? So lowercase z is from standard normal distribution, and just enter the probability from the top, the error probability on the right hand side. Then you are going to get this form. That is the definition of this notation, right? And then, so previously, this place we used 1.96, but now this is a general form because alpha can be any probability, right? And for whatever probability you use, just plug that in here, and then the margin of error has the same formula, same form. Like margin of error equals some standardized standard normal distribution number times standard deviation divided by square root of n, right? So remember, standard deviation is an estimator for the standard deviation, right? Anyhow, so this is the general formula. The For the confidence level of 1 minus alpha, the confidence interval should be the best point estimator x bar, plus minus margin of error calculated this way. Z value from standard normal distribution times standard error, right? So S over square root n is standard error of x bar, right? So the result is pretty simple. So that's all you need to calculate, right? So derivation is important, but just if you just get the broad idea, that's enough. But the formula is more important and simple enough to understand, right? Okay, so then think about this formula. So it depends only on 4 objects, right? The point estimator x bar, sample average, and sample standard deviation, right? And sample size, and some value from the normal distribution, standard normal distribution. Let's think about them. First, how does it move when x bar increases? The sample average affects only on the center, right? It determines the center, but does not affect the margin of error. Margin of error is fixed, but when x bar changes, the confidence interval moves parallel like this, right? The interval with the same length, but the center moves shifts to according to x bar. That's one thing. And second, sample standard deviation S. When standard deviation increases, that means the data is more variable. In other words, the data have more errors, more noise. So your estimator will be less efficient, or will be more variable too, because there are more noise. So your standard errors will be larger, your estimation error will be larger. So you need a larger margin of error. The margin of error increases when standard deviation increases. It is intuitive, right? As I said, higher standard deviation means more error, so you need more margin for the errors. And sample size. When sample size increases, you have better data. You have more information. Larger sample size is always better. So that means your estimator will be more accurate. The standard error of your estimator will be smaller, so your estimator will be more accurate. So you need only you can use smaller margin of error, right? You can minimize the margin of error because you are more accurate. And finally, this number depends only on the confidence level. So if you choose the confidence level, depending on the confidence level, it determines how wide your confidence interval should be. So how big the margin of error should be, right? If your confidence level is higher, then you have to have a higher coverage, right? To include more probability. So this value will increase as alpha decreases. By the way, alpha here is error probability. So alpha is smaller. If alpha is smaller, that means you allow smaller error probability. So you have to have a larger margin of error. So this is what I just explained. So again, the formula is simple. It only depends on 4 things, and you may interpret them intuitively. Okay. So and back to the common choices, you have simple choices like 90%, 95%, 99%. And we are going to use them many times from now on in this chapter and the following chapters. So let me summarize. So when you choose 90% confidence level, that means you are willing to sacrifice 10% as error probability. Instead, what you are going to get is you are going to get a smaller margin of error, so your estimator will be more informative. Anyhow, so if you choose 9%, that means error probability is 10%, and that means overestimation, the probability that true parameter is greater than your interval is 5%, and underestimation is also 5%. So overestimation, underestimation each has 5% probability. So as a cumulative probability, you need to find 95% from Excel. What you use on Excel is 95%. In the end, we usually approximate that number to 1.64. It's a common number. You are going to see this number in any statistics textbook, right? So these guys are associated with 90%. So if you choose 95%, you can do the same thing. Like error probability will be 5%, and overestimation, underestimation each has 2.5%, and cumulative probability CDF, cumulative distribution function, you need to find 97.5%, which gives you 1.96. Approximately, sometimes you approximate this to 2 as a rule of thumb, but I think 1.96 is more common approximation. 99% will have smaller error probability, and this is the result will be 2.58. So as you see, to increase the confidence level, you need to choose a higher value, which will increase the size of the margin for error, right? The margin of error should increase as the confidence level increases. By the way, larger margin of error is not desirable. It means your interval is less informative because it is too wide. Wider interval is less informative. So still you can see the trade-off between confidence level and the margin of error using these numbers. We are like with numerical approximations, you can see the trade-off. Okay, so this was mathematical derivations and common numbers. Next time, I'm going to use these numbers directly, right? Maybe I will briefly explain why we choose this, but you can just take this as granted, right? We did some practice earlier chapters, so I may go over these steps quickly. In the next video, I'm going to give you an example. So we have 2 more examples related to confidence interval. So they are coming in the next 2 videos. Okay, thank you for watching. See you later.